Another big problem with small populations is inbreeding, and this can lead to the loss of genetic diversity as well. So everybody knows what inbreeding is. It's the mating among close genetic relatives. So think siblings, parents and offspring, kissing cousins, that kind of idea. And close relatives are more likely to have alleles in common. Full siblings share about 50% of their genes on average. So I have a brother, likely, in all likelihood, he and I share about 50% of our genes. This is a problem because it increases the chance of an offspring inheriting two copies of a bad allele. So if there are two alleles that code for a disease, if somebody breeds with somebody way outside of their family, the likelihood of them getting two alleles for that disease is very low. However, if that allele is in a family and they keep breeding with other members of their family, it is likely that eventually there is going to be some offspring that have two copies of the gene for the disease, and they're going to express the disease and get sick. These offspring that are homozygous, so have two copies of the same allele, are less likely to survive and reproduce. So here's an example. These are snakes. We see that one parent is heterozygous, so has a big A and a little a. The other parent is homozygous, has two big A's. The big A's are fine. The little a is a recessive deleterious allele. So if you have two copies of this little a, you're going to get sick. So we imagine that these two snakes have three offspring. One is big A, one is big A, and one is big A, little a. And we imagine that one of these big A, little a's outbreeds with another individual that is homozygous for the big A. They're going to have an offspring that's big A, little a. If the two siblings breed, they could have big A, or big A, little a. But they also could have little a, where little a is not a possibility for this pair here or this pair here. And so this snake is more likely to be sick if there is inbreeding occurring. So the proportion of homozygotes, so two copies of the same allele, increases. So does the frequency at which deleterious recessive alleles affect phenotypes. The accumulation of these deleterious recessive alleles across generations is called the genetic load. So as we have more and more of these bad alleles that are recessive, meaning they're only expressed if you have two copies of them, we're more likely to get that with inbreeding. And inbreeding is more likely to occur in small populations because there are fewer individuals to breed with. So inbreeding depression refers to the negative effect that these deleterious alleles have on the average fitness of offspring in the population. So inbreeding is just mating among close relatives. Inbreeding depression is when mating among close relatives has negative effects. So you're more likely to have offspring that don't do very well. So here is an example in people. We know that inbreeding is bad and that we have a social stigma against inbreeding, and it's because of inbreeding depression. And we have seen this occur in some populations where inbreeding depression has been expressed. So this shows the mortality among children of first cousins and the mortality rate among children of unrelated parents in the same population. And if these were equal, then we would expect the mortality rate to not be affected by whether the children had parents that were unrelated or parents that were first cousins. But we see that the rate of mortality is higher in populations or from children of first cousins here than it is for children of unrelated parents. And this is an example of inbreeding depression in people. Those kids that come from parents that are more closely related are more likely to have deleterious alleles expressed, like I just said, and they're more likely to get sick from whatever that deleterious allele codes for, but some kind of disease. This is why we saw an increase in hemophiliacs in the Russian royal family back in the 1800s and early 1900s. That is a deleterious allele. That means that you don't have a blood clotting factor, and so if you get cut, you bleed and bleed and bleed. And that was a problem with inbreeding among royal families, which used to be more common because they didn't want to pollute their bloodlines with non-royalty. And we now know that that's a terrible idea, and that our offspring can be affected negatively from that. So, in populations that have passed through bottlenecks, both genetic drift, and inbreeding act to decrease the genetic diversity, which means those populations are less able to evolve into the future. Fewer mating options exist in small populations. With no immigrants, eventually all individuals will be related, and that will lead to inbreeding depression. And this is a problem for many endangered species. They get down to too low, and they may have no choice but to inbreed. One strategy to alleviate inbreeding depression is by the introduction of migrants from other populations, and we call this genetic rescue. So here's an example. So we see that this is the number of prairie chicken cocks, or males, here on this line. And up here is the percentage of eggs hatched. So when the population was relatively large and going up and down, the percentage of eggs that hatched was pretty high. Slowly, though, this population got smaller and smaller and smaller, and you can see eventually, slowly, the percentage of eggs that hatched was going down. Then there was a very low year. In this year, they introduced individuals from Minnesota to this Illinois population, and you can see this helped the population increase, but before that happened, the percentage of eggs hatching went way up. Basically, they think that introducing new genetic material masked whatever deleterious alleles were being expressed that was causing the eggs not to hatch, which means failed offspring if your eggs don't hatch. And that eventually this increase in reproduction led to an increase in the overall population size. So that's genetic rescue right there.